So in this section, we're going to be building off Hooke's law from 5.1 in order to extend our system of understanding from Hooke's law as applied to springs to more general systems that may obey Hooke's law, which forms the basis for 5.2 simple harmonic motion, using Hooke's law to define what simple harmonic motion is. So, simple harmonic motion is marked by two main characteristics. The motion must be periodic, meaning the motion will repeat after some time t, which we call the period of the motion. Okay? So, like springs repeat their motion after a certain amount of time, which is what we call the period. Okay? So that's where the harmonic part comes from, as harmonic means to be repetitive, so on and so forth. Okay? There's a nice harmony there. Okay? Or more specific terms, a nice periodicity, a nice repetition. The second condition that must be met, okay, is that the force acting on the object must be restorative, meaning that the force must depend on the displacement from the equilibrium position of the object, okay? The force attempts to restore equilibrium to our system, okay? So we must meet that mathematical condition where our force acting is directly proportional to the displacement from equilibrium, okay? So both of these conditions must be met. The motion must be periodic, and the force acting must be restorative, again meaning that the force must be directly proportional to our displacement from equilibrium. If one or the other of these conditions are not met, then the motion is not simple harmonic. So for example, it is possible to have periodic motion, to have an object that's undergoing periodic motion, but not simple harmonic motion because the force acting is not restorative. We'll take a look at examples of that in class and discuss what could be potential examples of periodic but not simple harmonic motion. So modeling and the mathematics of simple harmonic motion. Okay, so if you were to let a spring go, let's say you pull it up to a certain compression point and then you let it go, you notice the spring bounces back and forth in a nice periodic motion. Again, one of the features and hallmarks of simple harmonic motion. If you were to plot the position versus time graph of this object, okay, you would notice that it forms a nice sinusoidal graph as shown right here. Okay, so if we want to determine an equation to use to describe the position versus time of our object, a natural candidate to use is the trigonometric functions. Specifically, we use cosine. Okay. So what we say here is our position versus time graph, or the position of our spring here, is modeled as a function of time t by the equation a times cosine of 2 pi f of t. Okay? 2 pi f times t right here. Okay? We could use sine as well, but sine and cosine can be combined into one single cosine expression right here using a little bit of sleight of hand with trigonometry. Okay? So A represents what we call the amplitude, the maximum displacement from equilibrium. All right, so where we stretch, when our spring is fully stretched out or fully compressed, that represents the amplitude, where we're fully displaced from equilibrium, the maximum amount we can be. And then F is known as the frequency of the motion. It describes the rate at which the motion repeats itself. That may be a little bit esoteric and abstract, so we'll illustrate that with an example on the next slide. The units for frequency are 1 over seconds, or more commonly, we call hertz. So hertz are defined as 1 over seconds. Okay? So modeling the mathematics of simple harmonic motion. Okay? So in terms of what a position versus time graph would look like here for simple harmonic motion, again, it's going to look like a cosine wave or a sine wave. Okay? So what we can see is that the span between any two identical parts of the wave is what we call the period right here for our position versus time graph, because this is when we start out at one position, and then after this one cycle we come back to that original position. So this represents our period, the time it takes to complete one cycle of motion. The relationship between the frequency f and the period t is as follows. The period is defined as the frequency of, as reciprocal of your frequency, and vice versa. Frequency is the reciprocal of your period. Okay? So here's an example to make sense of what's going on with period and frequency, what I like to call the roller coaster analogy. So as an example to illustrate this relationship, please consider the roller coaster ride at right. Okay? If we complete 2 trips in a minute, we would say the period of the roller coaster is half a minute. It takes 30 seconds to complete one trip and then 30 seconds to complete the second trip, so 2 trips in a minute. So our period is 1/2 minutes. Okay? At the same time, however, our frequency would be 2 trips per minute because we're completing 2 trips in that certain amount of time. So we can see right here that our period and frequency are reciprocals of each other, the period describing how long it takes to complete a cycle, and the frequency describing how many cycles we complete in a certain amount of time. So let's look at an example with using simple harmonic motion and the mathematics of simple harmonic motion, specifically the position versus time equation we saw, in order to plot and analyze simple harmonic motion. So let's say we have a vertically hanging spring loaded with a 0.5 kilogram mass that is stretched 0.9 meters and then set into simple harmonic motion and is measured at a period of 3 seconds. We want to plot one full cycle of the motion of the object. Okay? So in order to plot one full cycle of the motion of the object, we do not need to write the cosine or sine wave. All we need to do is recognize that our graph is going to look like a cosine or sine wave, and then all we need to know from here is the amplitude and the period. So you do not actually need to write out the equation itself. So for example, okay, what we know here is our period is 3 seconds, and we know our amplitude is going to be 0.9 meters. Okay. So we're going to start at negative 0.9 meters, negative because it's being stretched. We have a vertically hanging spring, and it's being stretched, which means that the spring is being stretched below its equilibrium point. So our amplitude is going to we're going to start off at negative amplitude, so negative 0.9 meters, okay? So what's going to happen here is at 3 seconds, we're going to return to negative 0.9 meters because that's when we have one full period or oscillation. So now we're going to sketch a sine wave over this time interval. So at 1.5 seconds, we're going to be at 0.9 meters because that's the halfway mark of our period. So we're going to be fully compressed, and we're going to be at 0.9 meters, and then we're going to come back at 3 seconds to negative 0.9 meters. Okay? And this right here is all you have to do for plotting the motion. Now, let's say we do want to write the equation of the motion for the object. So the equation of motion is on your equation sheet, so you don't have to worry about memorizing anything, but there is a little bit more that you have to do here, okay? So we start off with the equation for the position versus time of a spring. Amplitude times cosine of 2 pi f times t right here, okay? In this case, our amplitude is 0.9 meters, and since the mass is stretched below, we must use negative a in our equation. So we're going to start off at a negative 0.9 meters. So negative 0.9 meters times cosine of 2 pi f times t. So all we need to do here now is to find our frequency in order to complete this equation. And that's where we take note of the period frequency relationship. That period is a reciprocal of frequency, so frequency will be the reciprocal of the period. So if our period is 3 seconds, that means our frequency is 1/3 hertz, okay? Thus, our equation of motion is going to be negative 0.9 meters times cosine of 2 pi over 3 times t, okay? And this right here is all we have to do to write our equation of motion. Lastly, we come to the period of spring. The period of spring equation relates to period, mass, and spring constant, okay? We'll describe conceptually how we get this equation in class, specifically why we have mass on top and why we have the spring constant on the bottom. Mathematically, we're not going to derive it because it involves calculus, so we're only going to look at the equation from the conceptual standpoint, okay? So we'll do that in class. So here, all we need to know for right now is the equation of the spring period, which is given as the period of spring is equal to 2 pi times the square root of m over k. Again, if you're wondering how we get this equation, it comes from calculus, but we can conceptually make sense of it, which is what we'll take a look at tomorrow in class with a demonstration. So, a quick example of period of spring. Students are designing an experiment to validate the above relationship. If they load a mass of 2 kilograms onto a spring with a spring constant of 50 newtons per meter, what should be the predicted period of the spring? So, using our known information in conjunction with the above equation, all right, we know we have to use an equation that contains a period of spring because, well, that's the problem is asking us for, and we only know one equation that contains a period of spring, which is this equation right here. So our period of spring is going to be equal to 2 pi square root of m divided by k, so we plug in 2 kilograms for m and 50 newtons for k, and that's going to give us a spring period of roughly 1.25 seconds. So for this specific problem, the students should expect to get a period of 1.25 seconds when they measure it experimentally, if this equation is correct, which it is.